Hello everyone. So previous classes we will see some introduction about the Bode plot and procedure for constructing the Bode plot. So in this class we are going to see one model problem, how to find the stability, gain margin, phase margin with the help of this Bode plot. Okay. So before going to the problem, just once again we will see that procedure for constructing this Bode plot. So we know that Bode plot is a frequency response plot consisting of two graphs. What are that? One is the magnitude plot and the second one is a phase angle plot. So first, for the given transfer function, we need to convert into the time domain, S domain to frequency domain, right? How to convert S domain to frequency domain? Just by letting S equivalent to J omega. And then we need to calculate all the corner frequencies. So please remember, for finding the corner frequencies, it should be in the standard form. That is 1 plus S T notation. Then we will get the corner frequency just by calculating 1 by T. That's it. You will get the corner frequencies. So for every term, we need to calculate the corner frequencies. And then based on the corner frequencies, we can allot the terms. Okay. So this is the way. First, we need to get the transfer function. And this transfer function will be converted to frequency domain by letting S equal to J omega. And then we have to arrange this table. So what is the table consisting of that? So what are the product terms in the transfer function? What are the corner frequencies of the product term? And what is the slope? And what is the change in the slope? Okay. So here, initially, we need to remember this point. What is that? The first product term is always either a constant term or an integral term or a derivative term only. Since first order and second order does not decide the magnitude at the initial frequencies, because at the low frequency region, the magnitude is 0 decibels. But only the either a constant or integral or derivative factors only constitute magnitude from the 0 point onwards. So that's why always a product term, first term is either any one of the given term from the transfer function. So for the terms, there is no corner frequencies. And the next remaining product terms will be assigned based on the corner frequency values. Okay. So and then we will choose one lower corner frequency, lowest corner frequency. So this value will be omega L. Omega L value should be, what is the condition? Omega L value should be less than the first corner frequency value. How much we can take means that's based on the problems. So omega L, it should be less than omega C1. Omega C1. So then at omega L1, omega C1, directly we can obtain the magnitude from the given product term. And from the remaining frequencies, we can follow this procedure. So how much change in the slope from present corner frequency to the previous corner frequency, and what is the gain at the previous frequency. Then we will get the corresponding gain value. So like that we will continue until that all the corner frequencies, and then we will take one more frequency, that is at highest corner frequency, omega h. So this omega h value which is greater than that highest corner frequency. So again we can use the same formula for this, so that we can get the all gain values. So then finally we can draw the graph. Okay. So let's see one model problem related to this. Here is a given question. Plot the Bode diagram for the following transfer function and obtain gain and phase crossover frequency. So we need to draw the first Bode plot, and then we need to calculate the gain crossover frequency as well as phase crossover frequency. Okay. What is the given function? G of s equal to 10 by s into 1 plus 0.4s into 1 plus 0.1s. So this is a given transfer function. Okay. What is the basic step? So first we need to convert this S domain to frequency domain. So that is G of j omega is equivalent to 10 divided by j omega into 1 plus j into 0.4 omega into 1 plus j into 0.1 omega, right? So here, how many terms, what are the product terms in the given transfer function? So shall I take 10? 10 is a one term. J omega is the one term. 1 plus j point 0.4 omega is the second term. 1 plus j 0.1 omega. No. So 10 by j omega itself, we can take that one product term. Which term it is? Is it constant or integral or derivative? 10 by j omega means integral term, right? So first we are having that one integral term. And the remaining are first out in the denominator. So that is 1 by 1 plus j 0.4 omega, and the second one is 1 by j plus 0.1 omega. So next we need to calculate the corner frequencies. Corner frequencies, what is the standard form? 1 plus st. st here. So that is 1 plus st. So what is the value of t? 0.4. So how we will get the frequency? 1 by 0.4, that is 2.5 radians per second. For this one, 0.1, 1 by 0.1. Okay, generally this is the formula for this omega c. Omega c is equivalent to 1 divided by t. So 1 divided by t means here the t value is 0.4s. Okay, so you will get the 2.5 radians second, and omega c is that 10 radians per second. So then how much frequencies you are having? 2.5 radians second and 2.5 radians second, and omega c is the 10 radians seconds. So can anyone tell what is the first term we have to write in this product table? Right. So first we have to assign the first term is always an integral term, because here what is the integral term? 10 by j omega will be the first integral term. So what is the corner frequency for this integral term? There is no corner frequency for the integral terms. Okay, here I will. So 10 by j omega. So 10 by j omega. So it is an integral factor. So there is no corner frequency. What is the slope of the integral factor? Minus 20 decibels. Okay, that we already covered in the previous classes. Once refer that. So for integral factor, slope is minus 20 decibels. Next, which term we have to assign? 2.5 omega. So that is 1 by 1 plus j 0.4 omega. So corner frequency is 2.5. So what is the slope for that first order in the denominator? First order in the denominator is also a slope of minus 20 decibels, right? And third one, 1 by 1 plus j 0.1 omega. So what is the corner frequency? 10. Again, it is also a first order in the denominator factor, so that the slope is minus 20 decibels, right? So then how we can get the change in slope? Okay, it's very simple. So just add all the values together. Here initially there is no slope in the slope change in the first product term. So you can write minus 20 itself here, no problem. Then minus 20 and minus 20. What is the total value? Minus 20 and minus 20, minus 40. And then minus 40 and minus 20. How much it is? Minus 60. Or else you can add here. Initially minus 20. And then next minus 20, minus 20, minus 40. Minus 20, minus 20, minus 20, minus 60. So in this way, we have to write that change in the slope in the last term. Clear? Okay. So please remember, always the first product term always occupy either integral term or derivative term or constant term. So in our given problem, there is a one integral term. So that's why we can assign that integral term. And there is no corner frequencies for those terms. And the next remaining terms will be assigned based on the corner frequency values. So what is the next step? We have to choose two frequencies. What are that? One is the omega L, second one is the omega H. Low frequency, high frequency. How we can choose the condition? What is the condition? For the low frequency, the value should be less than first corner frequency, that is 2.5. So omega L value should be less than the 2.5 and omega H should be greater than the 10. So here I am assuming this omega L value is 0.1 radians per second and omega H is 50 radians per second. Is it necessary to take the 50 radians? Means it is not necessary. You can take any value, but that is more than 10. So either 20, 30, 40, 50 like that. But how much value it will be required means, okay, we will see in the graph. Okay, then we need to calculate the magnitude. Next, we will calculate the phase. So for the calculation of magnitude, at what frequencies omega L, omega C1, omega C2, and omega H. At these frequencies, we are now going to calculate the magnitude values. So what is the first term here? 10 by j omega. So directly I will take this term, and for this term, I am going to calculate now what is the magnitude for that. Okay. So this is the term 10 by that's completed. So here, first at omega equivalent to omega L. So at low frequency, first we need to calculate the magnitude. So magnitude will be calculated for which term now? That means always for the integral term only, because that magnitude initially decided by this factor. That's why we will take this term directly. So we can convert into logarithmics. So that is 20 log of how much it is? 10 by j omega. So magnitude expression is 20 log 10 by j omega. So that is it. Now what is the value of omega L? Omega L is 0.1, right? So that is 20 log of 10 by 0.1. So 0.1, 10, how much it is? 0.1 means 1 by 10. So that is 100. 10 square. 10 square means you can write into 40 into log 10. So how much you will get? 40, 40 decibels. So next. And at omega C1 also. Until omega C1, the magnitude will be depends on the first factor only. Later, the magnitude will be dependent on the first and second factor. Until what frequency? 2.5. After 2.5 onwards, the magnitude will be depends on first factor, second factor, and third factor also. But until 2.5 frequency, because why? This product term, what is this product term? First note in the denominator. What is the general slope? 0 decibels until 2.5. After that only it has the magnitude, right? Coming to this one, until 10 frequency magnitude is 0. After 10 only, so here I'm writing. So 0 decibels and then only minus 20, right? What about this one? Until 10 it is 0. After that only it has minus 20. What about the first one? From the initial term onwards, minus 20. So that's why initially until the 2.5 frequency, it depends on only which term? This integral term only. That's why you are calculating that the magnitude value at omega L at omega C1 with the help of this integral term, 10 by j omega. So that is equivalent to 20 log of 10 by j omega. So we'll get omega value is 2.5. So then we will get the 12 decibels. So that means here onwards, now the first order factor will be coming into the picture. First one and second one. So then no need to calculate again with the help of this formula. So just we can get what is the change in the slope and what is the previous gain. Just by adding all the values, you will get. And please remember, Bode plots are approximation plots. So at omega equivalent to omega C2. So what is the formula for that? So how much change in the slope from omega C1 to omega C2 into log of omega C2 by omega C1. And what is the previous gain value at omega equivalent to omega C1? Okay. So what is the slope from omega C1 to omega C2? Omega C1 to omega C2. How much it is? How much change in the slope? Minus 40, right? So that is minus 40 into log of 10 by 2.5 plus what is the previous gain value? 12. So plus 12 decibels. So we will get that by simplifying. You will get the answer is minus 12 decibels. Okay. Next, we will take one high frequency. How much it is? Omega h is 50 radians per second. So then again we can use the same formula for that also. So slope from omega C2 to omega h into log of omega h by omega C2 plus the previous gain value at the omega C2 now. Omega C2 now. So what is the change in the slope? Minus 60 from omega C2 to omega h. That is minus 60 into log of 50 by 10 plus what is the previous gain value? Minus 12. So you will get the minus 54 decibels. Okay, these are the gain values. So 40 at omega L plus 12 at omega C1. Sorry. Omega L, omega C1, omega C2, and omega H. Clear? So for first omega L and omega C1, always we are calculating magnitude for the first term only. For example, here I am having the derivative term 10s, then I can take only 10 into j omega. 10 into j omega. For that value, we are going to calculate it. And so I said approximation plot. So without calculating these gain values also, we can draw the magnitude plot. How? See that? What is the initial slope? Minus 20. What is the next slope? Minus 40. What is the next slope? Minus 60. That means magnitude values are going to reduces, right? That means initially I can draw with the help of minus 20 and then from minus 20 to minus 40 and then minus 40 to minus 60. That means values are going to reduce. Initially, if I am having that plus 40, see that how much values you are having? 40. What is the next value? Plus 12. What is the next value? Minus 12. What is the next value? Minus 54. So that is from positive to negative, it will be going. Since slope will be changes from minus 20 to minus 40, minus 40 to minus 60 like that. That's the reason. So you can draw approximated plan. So with this magnitude calculations are over and then we are going to find the phase values. So what is the expression for the transfer function? Yes, we will go to the problem. So that is 10. 10 is constant. So that is 0 degrees only, right? What is the remaining term? Or else you can take directly 10 by j omega. 10 by j omega means what factor it is? Integral factor. What is the slope value for the integral factor? Minus 90, right? So that's why you can write directly minus 90 degrees here. Minus 90 degrees. And the remaining terms, 1 plus j 0.4 omega. 1 plus j 0.4 omega means tan inverse of 0.4 omega by 1. That is real part, imaginary part by real part. Here also, imaginary part by real part, which is in the denominator. So we will take into the numerator so that we will get the negative sign. So that is what is the phase angle? Minus 90 minus tan inverse of 0.4 omega and minus tan inverse of 0.1 omega. So just think that what is the minimum phase angle and what is the maximum phase angle we will get for the given bond. That is at omega is 0. What is the value? At omega equivalent to infinite, what is the value? What are the terms you are having? One is the integral term. What is the slope of integral term? Always minus 90 degrees, right? Give me 1 second. Integral factor. For the integral factor, slope is always minus 90, right? Second one. Second one. First order in the denominator. What is the slope of phase angle for the first order in the denominator? It is from 0 degrees to minus 90 degrees, right? Again, this is also first order in the denominator. So again, what is the slope? 0 degrees to minus 90 degrees. So that is maximum angle is minus 90, minus 90, and minus 90. How much you are getting totally? Minus 270. That means you will get that minimum value is 0 degrees sorry, minus 90 degrees, and the maximum is minus 270 degrees. So, but we don't want to calculate for all the frequencies. So the frequencies, all corner frequencies we are included here, and more than 3 values you can include between those corner frequencies. That is from 0.1 to 20. So then I can apply for this tan inverse of 0.4 omega and the same in tan inverse of 0.1 omega. Finally, we will get the phase angle. So here I will get that. So that is approximately minus 92, minus 118, minus 150, minus 170, minus 210. Sorry, it is minus 236. So from minus 90 to minus 230, you will get. So in this way, we are going to calculate the phase angles. Clear? So then we are going to draw the graph. So on the same graph sheet, we have to draw the magnitude plot as well as phase plot also. So let's see. Initially, we will draw the magnitude plot. So at frequency, what is the corner frequency you are assuming first initially? So 0.1. So I think you know how to represent the frequencies on that semi-log graph. So if I take the here 0.1, so 0.1, 0.2, 0.3, 0.4 and so on 1. So here 1, next decay frequency 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 20, 30, 40, 50, 60 and so on 100, 200, 300 and so on 1000. So 2000 and so on 10,000 like that, right? I hope it's already everyone knows that. Then take the magnitude values on this y-axis and the frequencies on that x-axis. So initially at the first, represent all of magnitude in the graph sheet. So at 0.1, what is the magnitude you are getting? 40 decibels. So that is 0.1. So the value is 40 decibels. Next, at 2.5, how much you are getting? It is plus 12 decibels. Plus 12 decibels. And then next, at 10 frequency, how much you are getting? Minus 12 decibels. And then last finally at 50, how much you are getting? Minus 54 decibels, right? So these are the values you can obtain and connect all the dotted lines with the help of scale. So from 0 to 2.5, sorry, 0.1 to 2.5, 2.5 to 10, 10 to 50. So but on the magnitude plot, we must represent how much change in the slope from one corner frequency to the another corner frequency. So initially, what is the change in the slope? Minus 20 decibels per decade. Next, from 2.5 to 10, how much it is? Minus 40. From 10 to 50, how much it is? Minus 60 line. So just we can connect all the lines and we have to represent the magnitude slopes on the magnitude plane. Next, in the same graph sheet, again frequencies on the x-axis and phase angles will be taken on the y-axis in this side. Phase angles will be taken in this side, on the left side. So it's easy to remember, easy to represent the values. So see this, what is the maximum angle you are getting? Minus 240, right? So take the last value itself, minus 240 here. So minus 240. So then based on our values, you can take the scale, either it is a 10 units or 20 units or 30 units based on the problem. So here I am taking that every unit is a 20 degrees. So that is minus 240, minus 220, minus 200, minus 180, minus 160 and so on until what value you are requiring? Minus 80, minus 92 will be sufficient. Then represent all the values across 0.1. It is approximately 90, 92 degrees. Okay, I will represent with another color so it is easy to identify that. So for that phase plot, so just refer the values. Then at 0.1 frequency, you will get that minus 92 degrees. And then next at frequency 1, you will get that approximately 118 degrees. And then 2.5, it is approximately minus 150 degrees. And then at 4, you will get that minus 170 degrees. And then at 10, it is around minus 210 degrees. And at 20, it is around to 36 degrees. Okay, previously I said, what is the omega h we have to choose means, so while if you want to calculate either the gain margin or phase margin, that has to be calculated at gain crossover frequency or phase crossover frequency. So what is the minimum requirement means, magnitude value should be in the range of 0 decibels and the phase angle in the should be in the range of minus 180 degrees. Suppose if I am for the 10 at the 10 frequency, highest corner frequency, you are getting here minus 200. No problem. It will cross that, exceed the minus 180. For example, it is not exceed that 180 at the frequency 50. Let us assume at 50 angle is minus 170 only, but we need minus 180 degrees. So that I need to take that one more value, that is approximately 100. So maybe that time it crosses at minus 180 degrees because the required angle is minus 180 degrees. That's the reason. Based on that, you can adjust that high frequency value. Okay. And face plate will be drawn with the free hands. Okay, face plate will be drawn with that free hands only. So, and last one, we need to calculate the most important here, gain margin and phase margin, right? Gain margin and phase margin. First, we will see that, sorry, gain crossover frequency and phase crossover frequency. So, what is the meaning of the gain crossover frequency? Gain crossover frequency indicates that at the frequency, the magnitude value is 0 decibels. Okay. So simply what you're doing across the 0 decibels line, we are extended that 0 decibels line towards on the, it will touch this magnitude plate at some frequency, right? What is the frequency, corresponding frequency? Simply extend this line towards the frequency. So exactly it will touch that at a frequency of 5. That is at omega GC value, the magnitude is 0 decibels. Then the frequency of 5 radians per second will be known as the gain crossover frequency. Okay. So once again, the condition for the gain crossover frequency is the magnitude should be 0 decibels. Simply take one line from the 0 decibels and extend this line. It will touch the magnitude plot at some point. So at what point it will touches, from that point, extend that line towards its frequency line and then corresponding frequency you have to represent. So that is that 5 radians per second. 5 radians per second. 5 radians per second. And similarly, if phase crossover frequency. What is the phase crossover frequency? The frequency at which the phase angle is minus 180 degrees, right? Omega p is phase crossover frequency. The frequency at which phase angle is minus 180 degrees. So then we will see the phase plot now. I will erase this one. Phase plot now. So from the phase plot minus 180 degrees, just take this minus 180 degrees and extend one line, dotted line only, not dark lines. Extend this line. So this will touch that at phase plot. At what point it will be touch the phase plot? From that point, just extend this line again towards this frequency range. So again, what you are getting? At again 5 radians per second, the phase value also minus 180 degrees. That is at omega GC is 5 radians and omega PC also 5 radians. That is gain crossover frequency value, phase crossover frequency value should be same. Okay. Okay.